Let's continue with these examples. Next we have x is equal to 0, 1, 2, 3, 4, y is equal to 6, 7, 8, 9. I use this example to give you, give you an example of what of two sets that are mutually exclusive but not collectively exhaustive. We saw this example earlier, and so if we use a general two set Venn diagram, what's gonna happen? I have my two set Venn diagram, x and y. Is there any element that is present in both x and y? There isn't, so leave it blank. So x is 0, 1, 2, 3, 4. Y has 6, 7, 8, 9. What have we not written? We have not written 5. That's outside the union. Now this is basically mutually exclusive because the intersection is empty. It is not collectively exhaustive because the outside of the union is not empty. Now we don't need to draw this general two set Venn diagram with the 4 regions. We can draw a version without the empty region. What does that look like? Two disjoint sets, because the intersection was empty. Let's draw them without an intersection. So we have x and y, 0, 1, 2, 3, 4, 6, 7, 8, 9, 5 is outside. Notice that the skeleton of this Venn diagram without the numbers and the names, the circles and the square looks just like the previous case of R0, R1, R2, which is a ternary partition. That's because this is also a ternary partition. When you have two sets which are ME but not CE, you can just add a third set that is missing, that gives you the element that is missing in both sets. I'll just put W is equal to set 5. Notice that now I have a ternary partition. X and Y were already ME, they were not CE. The part that was missing was 5, and I made a third set with the element 5. Now we have a ternary partition, which is why this diagram looks the same as the previous diagram with R0, R1 and R2. Let's look at the next one. It is x is 0, 1, 2, 3, 4, z is 4, 5, 6 and 8, 9. I'd given this as an example of sets that are collectively exhaustive but not mutually exclusive, because 4 is common to both of them. Now what does this look like when we put it in a general two set Venn diagram? That's my general two set Venn diagram. I have my x, I have my z. 4 will go here, 0, 1, 2, 3 will go here, 5, 6, 7, 8, 9 will go here. There's nothing outside the union. Outside the union is blank. Now typically we don't use any other simplified Venn diagram for this kind of a situation. We simply draw the general two set Venn diagram and leave the outside blank. That is all. But if you want to do something, it can be done. What would that look like? I'll take my universal set. I will draw my x like this, and then I'll draw my z like this. Notice that this was x, this was z, and what do you get as the elements? 4 will go here, 0, 1, 2, 3 will go here, 5, 6, 7, 8, 9 will go here. This region represents x, z bar. This region represents x, z. This represents x bar, z. And x bar, z bar, the empty region in the general two set diagram, that region has been eliminated from this diagram. This can be done if you are very particular about not drawing an empty region, but nobody does this. I don't recommend doing this. Just saying it can be done if you really want to do it. There's one last case to consider, which is the subset superset case. The example that I'm taking is the set M2, which contains the multiples of 2, 0, 2, 4, 6, 8, and M4, the multiples of 4, 0, 4, 8. what does this look like, M2 and M4 in a general two-set Venn diagram? I have my two-set Venn diagram. I have my M2, M4. So the intersection of M2 and M4 contains 0, 4, 8. What element is present in M4 but not in M2? There's nothing there. This segment is the empty segment here. What is present in M2 but not in M4? 2 and 6. So that's basically all of the even numbers, and the odd numbers 1, 3, 5, 7, 9 will be outside the union. So you have a general two-set Venn diagram with 4 regions. One of the regions is empty, and there is some sort of dependence between the memberships here, but not in all cases. So let me elaborate. If I was thinking of one of these 10 numbers and I told you that is present in M2, you would not be able to predict whether it's in M4 or not. But if I told you it's absent in M2, you'll be able to say it is absent in M4. And going in the other direction, if I told you it's present in M4, you can tell me that it's present in M2. If I told you that it's absent in M4, you will not be able to predict whether it's in M2 or not. So there are some cases where you can make the prediction and some cases where you cannot. This is different from the MECE binary case that we saw first. But you notice that there is at least one case where predictions can be made, and so at least one segment of the general n-set Venn diagram will be empty. And what we do with this, we have already seen. You draw a circle inside another circle. What does that look like? So the idea is basically you have your M2, which is a larger set. You have your M4, which is a smaller set. This is your general two-set Venn diagram. But this portion right here is empty, so there's no need to draw that outside. So you move that circle inside and you keep it like this, and then you have your universal set, and you have M4 0, 4, 8. M2 has an additional 2 and a 6, and outside M2 is your 1, 3, 5, 7, 9. This is what we do with the subset superset case. These are all examples of cases where you don't need a general n-set Venn diagram because some of those regions are empty.